the work which we did at IIT Madras, since I was the assistant professor in mechanical to start with, is mostly directed for mechanical measurements like length, deformation, and so on. So you will find that my work slightly departs from the physics domain, but makes use of a lot of physics. I'm going to talk about speckle metrology. So basically, speckle metrology is a measurement technique that makes use of speckle phenomenon. And we need to understand what is the speckle phenomenon. So this is roughly the contents of my talk. I'll introduce the speckle phenomenon, talk about the property of the speckles, then the techniques which we used, some of them we developed. These techniques have been grouped under two different categories. Earlier, we used to use photographic film for recording, and therefore they are under the group photography. And later on, we started using VDCOM camera, then CCD camera, and then they were transformed to be used with CCD and VDCOM. Then I will say a little about how we process the data, some of the applications of the metrology will be dealt with as I go on. But the subject being so wide, it's very, very difficult to touch upon everything which can be done. But once I introduce the principle, you could probably figure out what could be other possible applications of the technique. Now, how is the speckle formed? You shine a beam of laser of any color on a diffusively reflecting surface. It's a diffuse surface, it's a rough surface where the roughness is of the order of wavelength of light or more, and in a space is formed a pattern which we call a speckle pattern. This is formed in the whole space. It has a structure. I will talk about that. And the process behind that is multiple interference, multiple beam interference or multiple wave interference. And you can record this one either on CCD or linear array. If you are recording on CCD, you can scan a line and see how the intensity fluctuates. It's a random pattern. It's completely random pattern because it is now determined by the surface roughness, which is random. These are some of the earlier works, because people studied scattering from the pollen particles, from the colloidal solutions. The scattering of radio waves from ionospheres also generates a speckle pattern. But the real application and real acceptance of this phenomena came after the lasers were being used in the laboratory. Although the first laser appears in 1960, but many of them came in the laboratories around 61, 62. People started doing holography with, and then they found that all holographic reconstructions were submerged in noise. This was a speckle pattern. And first explanation of this, how it is formed, was given by Rigdon and in 1962. And then people started thinking how to suppress this noise. And they found various means of doing it. People also developed the statistical theories. Goodman has written a book on this. In 1968, Giroh came up for the first time that we could utilize it for measurement. An application of that one as an eye refractometer was patented in 1970. Then speckle interferometry was used to compensate for the atmospheric turbulence. Earlier, what happened? Earlier, the recording was video recording, analog. That continued from 1971 to 90s. And later on, it became digital. So, as I mentioned, holographic reconstructions were immersed in noise. It was considered a bane of holographers. And Rigdon and Gordon in 1962 gave an explanation how it is formed. And the first application of speckle pattern was presented by Grove. Engineering uses of laser-produced speckle pattern. And that emphasizes laser-produced because the speckles were observed even at microwaves and so on. And this was the birth of the speckle metrology. It's fairly old technique now. You could say 50 years old. We can also celebrate the intensity or probability density of intensity. Intensity is a misnomer actually. Now we don't use intensity, we actually use the word irradiance. But most of the earlier books use the term intensity. That follows negative exponential function, which means most of the regions in the speckle pattern are dark. As you have seen that, you had bright spots and most of the regions were dark. And the mean contrast of the speckle, if it is fully developed means it has to be created from a surface where the RMS value is more than wavelength and the light is linearly polarized. In that case, the contrast of the speckle is unity. It has also been used to measure roughness of the surfaces, provided the roughness is less than a wavelength, and there the contrast is taken as a measure of roughness. So you can see that the contrast varies depending on the surface quality of the object. We define the mean size by the autocorrelation. You have the speckle pattern, you autocorrelate and find the size. And we use the same kind of technique for the measurement of deformation or shift or displacement. Displacement, I will use a term when it is a constant value. Deformation when it varies, but deformation is also a displacement. And in order to find the displacement position and magnitude, we do the cross correlation kind of stuff. This is one of the important parameters. Although the picture shows a random distribution, but we still assign a size to the speckle. Now in the picture here, you will see two different kind of experimental arrangement. One is a free propagation, where the laser shines on the object and we observe a speckle anywhere in space. And the speckle has a finite size, both in transverse dimension and the longitudinal dimension. In the transverse dimension, it is lambda over alpha, where alpha is the angular substance made by the illuminated portion at the location where we are making an observation. And as we go away, the speckle size, the transverse speckle size will keep on increasing. And it has a longitudinal also, which goes as inverse of alpha square. So as we go farther away, the longitudinal size shrinks much faster than the transverse size. We normally don't use this geometry for measurement because I cannot really relate the location of the speckle to the location on the object. And therefore, we use a geometry which we call as image plane. We look at the speckle at the image plane of the object, and there it is governed by essentially the F number of imaging lengths. Here you can see it makes a substance beta. This substance is by the lens, and the transverse size is lambda over beta, and longitudinal is lambda over beta square. And since it depends on the size of the lens being used, we could control here the speckle size. This is one of the beauty of using this, and we make use of in our experimental setup. But recording is done on a plane, so we really don't record the whole longitudinal speckle, but a section of that. Now, what happens when the object is subjected to external forces, which means an external force may be such that it simply moves it, or an external force could be such that it deforms. Three things may happen. The speckle itself may move, and it does happen when we move the object bodily. The speckle irradiance changes. Since the speckle is formed by multiple wave interference, and the moment I deform the object, I change the relative position of the scattering centers, and thereby the phases of these waves, and hence the speckle irradiance will vary. And both these effects take place. We usually avoid this last situation for doing the measurement, but in some cases we cannot, and we have to live with it. The techniques in spectral metrology have been classified in 4 different ways. I have put them. It's a speckle photography, where we record the speckle, either on film or on CCD, but it's just a recording of the speckle. And when the object changes, we make another record, and from these 2 records we can do processing. I will mention as we go further how it is done, but this is how we can obtain the value of the displacement and so on. In a speckle interferometry, we intentionally add a reference beam. Although the speckle pattern in itself is multi-beam interference, but in order to have some kind of reference to start with, we add a reference beam or reference wave, and therefore we have now an interference between a speckle field and the light wave, reference light wave, and this is what gives rise to speckle interferometry. We can also carry out the shear part. Shear means we displace the image of the object in such a fashion that we can obtain the derivative of the phase function. And when we use CCD or VDCon, The same technique is termed as electronic speckle pattern interferometry, and we have a shear part of this one, electronic speckle pattern shear interferometry. The last one actually was developed by a student Jonathan at the University of Stuttgart, and what he did, he recorded a series of specklograms by varying certain parameters continuously. And with that, he was able to generate several. He generated many papers, but it was a wonderful work, and I thought this technique requires a special mention. Now, here I'm talking about speckle photography. And what we do, we make an image of the object. It has been done here on photographic plate. And when you move the object in its plane, that is why I call it, it's sensitive to the in-plane motion, then the speckle pattern as a whole moves. So we used to record 2 exposures on the film. And this double exposure specklegram later was processed using 2 different filtering techniques. One is a point-wise filtering, where you use a narrow beam and look at different portions of the specklegram. Each portion will generate what is known as a Young's fringes, that is due to the 2 identically displaced speckles. And by measuring the distance between the specklegram and the image plane, wavelength of light, measuring the fringe width, you could find at that particular point how much the speckle has moved. And if you do it at large number of points, you generate a kind of displacement profile. You could also do it by what is known as a whole field filtering. And this technique generates the fringe fields over the whole object, and from there you can find the displacement. The sensitivity is controlled by this little hole, which is the filtering aperture. Its location determines the sensitivity, which means how many fringes you could get in the on the object. If you do a shear part, you create 2 images of the object. And in order to create 2 images, we used to put a tiny wedge in front of one of the aperture. So you see, the object is being imaged via the light passing through these tiny apertures, and the wedge displaces these 2. And this creates 2 when we do the processing, 2 point-wise filtering interferogram which interfere, giving you the second derivative information. Now, in speckle interferometry, as I mentioned, we have to add a reference wave. And this reference wave could be a diffuse one or a specular one. It's added at the recording plane. The interesting part is, by the angle between the object wave and the reference wave, we can also control the size. And since we make use of the CCD or VDCon, which have a much lower resolution than the photographic plate, the reference wave is normally added along the axis, which means it is along the axis of the imaging system. But the beautiful part of the speckle interferometry is that I can organize, configure the experimental setup so that I can measure only one displacement component. Those of you who have done holographic interferometry, you will notice that the hologram or in hologram interferometry, you record the displacement vector. You cannot really sort it out which component you are recording. And in order to retrieve that information, you have to do processing at multiple directions and so on. It's much more complicated thing. Here I can have a setup which will give me only one component of the deformation vector. We can introduce phase shifting, which means we can now generate the phase profile rather than analyzing the fringe patterns. We can vary the sensitivity. Sensitivity can be varied, as I will show, by several ways. Wavelength is one, but which we seldom use. And we can record displacement components and its derivatives simultaneously, which means I can have shear and normal interferometry at the same time, and can be used for making the shape measurements, contouring or the measurement of the shape. This is basically the whole idea behind it. You have a speckle pattern from the undeformed surface. You have a speckle pattern from the deformed surface. You subtract one from the other, and it generates the fringes, which are due to the motion of the speckle pattern, or due to the radiance change of the speckle pattern. And these are the interference fringes which we make use of to find the deformation. This is for a case where we have a diaphragm which has been centrally loaded, so you have a symmetric circular fringes. This is the governing equation. It is used in holography. It is used in a somewhat different way in interferometry as a whole. Whether I talk about Michelson interferometer or Rayleigh interferometer or Mach-Zehnder interferometer, everything is within this diagram. K1 and K1 plus delta K1 are the propagation vectors in the illuminating beam. And K2 and K2 plus delta K2 are the propagation vectors in the observation direction. And D is the deformation when the object in its initial position is deformed by an external agency to a new position. So D has got these three components, dx, dy, dz. When we work it out, we can actually say that the path difference due to the deformation can be expressed as K2 minus K1 with a dot product with the deformation vector. This is the phase difference due to the deformation, and when it is a multiple of 2 pi, we get a fringe formed. Here I can change K2, I can change K1, I can change wavelength. And therefore we can have different configurations, and that is what we are going to look at. This is in-plane displacement measurement, which means in this kind of arrangement, I sense only the in-plane component. The object is in XY plane, and G direction is in the along the optic axis. And if you put all these things, you will find that the delta is the function of x component of the deformation vector and sine of the angle. And here also the x component of the deformation vector and the sine of angle alpha. Obviously, this alpha is much smaller. Here, theta can be varied a lot. And therefore, these two techniques have different sensitivities, but they are configured just to give you an in-plane displacement component. This technique is known as a Linder's method. This is known as a Duffy method. And they both can be combined. As you can see, both can be combined, and you can have a setup with a low sensitivity to a very high sensitivity. And here, this has been a little arithmetic just to show you that this is the low sensitivity part is the left side picture of the cantilever, which has fringes, and the right side is where we have given a large deformation, and we see fringes only where there was light in the left side picture, you know. So the fringe pattern. One can work out and see how it happens. Okay. This particular arrangement you see in both is a Michelson kind of arrangement. We call it as a Twyman Green interferometer because in this form it is used for optical testing. And a Michelson normally doesn't use a collimated beam, but it's a Michelson interferometer setup. And the same kind of setup we can use with these two apertures. They have different advantages. Here, this is sensitive only for out of plane. Michelson is completely out of plane because once you put it in this equation, governing equation, you see it senses only the G component. And this right side one, it has both the components. And depending on theta, you can make it less sensitive for the in-plane. And if you can come along the axis, it becomes sensitive only for out of plane. But this kind of arrangement, which was shown to the right, it has a much better explanation. The speckle size is governed by the aperture here. How big is this pinhole or hole through which the light goes, through which the imaging is taking place? That decides the speckle size. And the separation between them decides the number of fringes within each speckle. So each speckle is modulated. This kind of arrangement later on has been used for spatial phase shifting. But when I do the whole field filtering, I create, due to the fringes in each speckle, a pattern which gives rise to me a central halo and the side halos. And the side halos give you a clean interference pattern without any speckle background. We have used a different kind of configurations. If I use 4 apertures in front of an imaging lens, this becomes sensitive to X and Y components. I can extract X components from these green halos and Y components from this bluish halo. And it is not necessary that I use 4. I can use 3 of them. The halo distribution changes, but I still have halos which can give me X and Y components. And if I want to have a G component, I put a ground glass, and that ground glass is illuminated by another beam, and this generates a reference beam. So that now I have G components coming from this deep blue, Y components from this light blue, and green components from the X components from the green halo. We use several shearing methods. And I have put them under 5 different categories. Lateral shear or linear shear, where the object itself is linearly shifted. Rotational shear, which is rotated with respect to the center axis. Radial shear, where you have 2 images of different sizes but centered. Inversion shear, where one is inverted with respect to the other, and the folding, where it is folded about either x-axis or y-axis, and depending on that, you get different kind of fringe patterns. Well, this is one experiment which was done on a pipe, where here we have out of plane displacement fringes. This is kind of arrangement. 2 wedges are put in front of 2 holes. This is the middle hole and a ground glass plate, and we extract fringes from various. So as you can see, the middle picture is derivative of the. We have a little defect here, which is a circular thinning of the plate or thinning of the pipe. And here you can see these fringes are too fine and too close. But once you take a derivative, you get these slow fringes. And this is the y derivative, and the middle one is the x derivative. Now I will shift over to using CCD and see what we can achieve. CCD speckles are generated by coherent illumination. That is the normal one we were doing it using laser light. But nowadays, another technique has come into practice, which is used very often in study of rotating systems and so on. That is a digital image correlation. Here, the speckles are artificially produced. And one of the simplest way one does it, take a brush, dip it in black paint, and shake it on the object. You know, you generate black dots on that. You know, this is how the speckles are generated. And both of them are used invariably for in-plane measurements. But if you want to use it along with in-plane and for the out of plane also, you have to use 2 cameras, sometimes 3. There are certain assumptions which are there that speckle size has to be larger than the pixel size which we use for the in the CCD. The speckle displacement is to be greater than its average size, so that you have at least 2 separated speckles. And speckle displacement must be much smaller than the aperture of the illuminating system. Otherwise, there will be so much of decorrelation that you cannot really extract any information. And measurement process is just to take the cross correlation. This is how the cross correlation is taken. At 2 different points, you just carry out this kind of mathematical operations. There are softwares, you know, just to do all this. Here is a picture, what it shows. There are 4 speckle glands, 1 undeformed object. The B is where it has been deformed by a little bit, it's moved. The C1 is little more, D is still more, and you do the cross correlation. The first one is autocorrelation. You get a bright peak which determines actually the speckle size, and then here you get these cross correlation peaks, you know, and their separation gives you a measure of displacement. What is good part about the speckle pattern interferometry? You can, in photography, I have to record one after the other. So both the both the patterns are on the same plate, recorded one after the other. And there is no way I can individually handle them. In case of a speckle pattern, they can be handled independently. You record it, store it, record another one, and then you can manipulate the way you want. You can do either additive, SPI, subtractive, ESPI, or multiplicative, where you multiply these things. You can match the speckle size by changing the aperture of the lens. You can collect the data at video rate, and if you have a fast camera, you can do it much better. And therefore, transient events can also be studied. It's very difficult to do transient events of photography. This is the kind of setup we have. As I said, we come with a reference beam which comes axially, make an image of the object. This is my K2 vector, this is my K1 vector, and due to deformation, there is a phase change delta introduced, and this delta we calculate in terms of K2, K1. So we can make the setup as we want. Now in additive, we add these two patterns, and the resultant intensity is given by this. And since the monitor gives you, monitor will not record this negative going part, we actually square it, and this is how the brightness on the monitor appears. So these are what is called as the cos square fringes, which are embedded in the speckle noise. At the same time, A has a strong background. In the subtractive, this background has been completely removed, and we carry out the same process, square it, and here we have the fringes which are sine square delta by. You can see here in additive, when the phase or those part of the object which have not deformed, delta is 0, they appear bright. And in subtractive, they appear dark. So one has to understand what one is doing. And multiplicative, you get several fringe patterns. You have one due to pure cos delta, another you have due to cos delta by 2, where alpha, beta, but you generate a kind of pattern, which is normally not used. We mostly use subtractive because it frees us from the background speckle noise. Here are some pictures, for the out of plane measurement, So here the illumination is along the axis, and this is a picture of the weldment where two plates were welded, and it shows, discontinuity at the welded place. People have started using holographic elements also as a part of the optical configuration, and arise with TZT to introduce phase shifting. This was one experiment we did in the beginning itself, a long time back, maybe in the 80s, to find the Poisson's ratio of different materials. We use a 4-point bending and software cursor, which will measure the angle and give us the value of the Poisson ratio. This kind of arrangement is used for measuring in-plane deformation. One of the person in, I think he's in Brazil, they modified it to measure the in-plane deformation in a gas pipe. And you see he's making use of holograms, making use a mirror to illuminate with two plane beams from both sides, and collects the light, send it to the CCD, and phase shifting and everything was introduced. It's a very small kind of system. This was done again by us to look at the crack, what happens, when we do the in-plane loading. This is the in-plane sensitive system, and U is the in-plane components. This picture shows when you drill a hole, there's a lot of stress. And how do we measure? We measure it by relieving it. So we do in a plane electronic speckle interferometry, and this one gives me the U contours, and this one gives me the V contours. And here was a small crack. We used the in-plane sensitive configuration, but the object was loaded transversely, not an in-plane loading. But you can see how the fringes develop and show you the presence of the defect, crack. These are some of the modern configurations which have been used. In one system, people have used this aperture plate followed by a polarizer, so that the different recordings, although they are carried out at the same time, they do not interfere with each other. That is why these different polarizers are used. And in other configurations, a fiber optics is used, but in order to get all the three components, 3 cameras have been used. So here you see there are 3 cameras. Feed is by fiber optics. Here is also fiber optics, but three cameras have been used. We can look at the vibrating objects and see what kind of processing goes on. This is the intensity distribution. One observes, here was a delta, and this delta, depending on the setup and the vibration, amplitude A and the frequency omega has been inserted here in place of delta. And then you carry out the recording over a certain period, time t. This is your record. And this record, when you carry out this, gives you a J naught. But I want to have only the fringes part. So we do some kind of manipulation. We subtract I1 average from the I1, and then create another I2 by adding a phase 5, like it has been done over here.
Sir, your microphone is...
Sir, you got muted. Your mic got muted, sir.
You just write it, otherwise he cannot hear probably.
SIROHI sir, your mic is muted. Sir, please unmute. SIROHI sir.
You send a message. Probably Shankaran can open it.
Sir, I think somebody else has muted his mic.
Oh, sir.
Now it is clear. Now it has come.
What message? It's all gone. Anyway, thank you.
Okay.